You've probably wondered about it, right? Why does oil just float on top of water, but a spoonful of sugar seems to vanish into your tea? Well, today, we're cracking the code on the chemistry of mixtures. We're going to dive deep into what a solution really is, how scientists measure them with mind-blowing precision, and the simple rules that decide why some things mix and others, well, they just don't. All right, so let's kick things off with a little puzzle. Picture two beakers. In one, we're stirring sugar into water. In the other, we drop a piece of aluminum into acid, and you see all this fizzing as it dissolves away. Now, they both kind of look like they're mixing, but believe it or not, only one of them is what chemists call a true solution. So which one is it? And the secret? It all comes down to the difference between a physical change and a chemical one. See, when sugar dissolves, the sugar molecules are just spreading out. It's still sugar, just mixed in with the water. That's a physical change. But that fizzing with the aluminum and acid, that's your dead giveaway. It's a chemical reaction, creating totally new stuff. So a true solution is always about physical mixing. And that means the sugar water is our winner. So what is a solution officially? It's a homogeneous mixture. Now, homogeneous is a bit of a sciencey word, but all it really means is that the mixture is the exact same all the way through. The sugar is spread out so perfectly in the water, you're never going to see it settle at the bottom. Every single sip of that sweet tea tastes exactly the same, from the top of the glass to the very last drop. That's what homogeneous means. Okay, to really get how these solutions work, we need to meet the two main characters in the story. Think of every solution as a kind of partnership with two key players, and each one has a very specific job to do. And those players are called the solute and the solvent. It's simple, really. The solute is the thing that gets dissolved, so in our example, that's the sugar. And the solvent is the thing that does the dissolving. That would be the water. The way I like to remember it is the solvent kind of solves the problem of the solute. And you'll see in a second, it's all about what they do, not how much of them there is. Now, here's where we need to bust a common myth. A lot of us learned back in the day that the solute is just the ingredient you have less of. But that's not quite right. The real pro-level definition is all about the action. The solute is what gets dissolved, period. The solvent is what does the dissolving, period. It doesn't matter which one you have more of. Okay, so we know what a solution is made of. But how do we talk about it like a chemist? I mean, we need to move past just saying a drink is strong or weak and get into the world of actual, precise measurements. Just think about making a powdered drink. You pour in a full packet and you get this really strong, dark orange juice. You use half a packet and it's weak and pale. You just know the difference, right? You can taste it. Well, chemists need a way to put a number on that strength. And that's a property we call concentration. But that brings up a massive problem. To measure concentration, you need to know exactly how much stuff, how much solute, is in your solvent. But you can't just sit there and count atoms. I mean, they're impossibly tiny, and there are literally trillions and trillions of them in even a small sample. So how on earth did scientists get around this? They came up with an absolutely brilliant idea called the mole. The best way to wrap your head around it is to think of it as the chemist's dozen. You know how a dozen is always 12 of something? Could be a dozen eggs, a dozen donuts. It's always 12. Well, a mole is the same idea. It's just a word for a very specific and very, very large number of particles. It's just a way to group them up so we can actually work with them. And there it is. That's the number. It's called Avogadro's number. And yeah, it's pretty mind-boggling. It's a 6 with 23 zeros after it. But by defining one mole as this exact number, chemists built a bridge. Now they can just weigh something on a scale in grams and know exactly how many moles, and therefore how many actual particles they have. It's genius. It makes the invisible world of atoms visible. So, armed with this amazing tool, the mole, we can finally get down to business and measure concentration with real numbers. Now, the two most common ways to do this are called molarity and molality. I know they sound almost exactly the same, but that tiny little difference between them is actually a really big deal. First up, we have molarity with an R. So the formula here is the moles of your solute divided by the liters of the entire solution. This is super common in labs when you need to make, say, exactly 1 liter of a specific mixture. But here's the catch. You know how things expand when they get hot? Well, volume changes with temperature, which means a solution's molarity can actually change if the temperature goes up or down. And then we have its cousin, molality, with an L. Look closely at the formula. See the huge difference? It's the moles of solute divided by the kilograms of just the solvent, not the whole solution. And what's the one thing that doesn't change when you heat something up? Its mass. So molality is totally independent of temperature, which makes it super important for experiments where temperature matters, like studying boiling points or freezing points. All right, so we've covered what a solution is and how we measure it. For this last part, let's get into the final piece of the puzzle, the fundamental rules that explain why some things dissolve in the first place, and why there's always a limit. So picture this. As you start adding sugar to your tea, the solution is unsaturated, which just means there's still room for more sugar. But eventually, you hit a point where no more will dissolve. You can stir all you want, but you'll just see crystals at the bottom. The solution is now saturated. It's full. But there's a cool trick. If you heat it up, sometimes you can force even more sugar to dissolve, creating a really unstable, supersaturated solution. Now, that limit, that exact point where a solution gets full and becomes saturated, isn't random. It's a specific, measurable property called solubility. Basically, it's defined as the absolute maximum amount of a solute you can cram into 100 grams of a solvent at a certain temperature. It's the number that tells you where that saturated point is. But why is there a limit? And why can you dissolve tons and tons of salt in water, but basically no oil at all? Well, it all boils down to one of the most simple and powerful rules in all of chemistry. And it's this: like dissolves like. Now, to get this rule, you just have to understand a concept called polarity. Think of polar molecules, like water, as having a slightly positive end and a slightly negative end. They act like tiny little magnets. And then you've got the opposite, nonpolar molecules, like oil. They have an even charge all the way around, so they're electrically neutral. No magnetic poles at all. So when we say like dissolves like, the like we're talking about is polarity. It's really that simple. Polar things with their little magnetic ends are great at pulling apart and mixing with other polar things. And nonpolar things are perfectly happy mixing with other nonpolar things. But when you try to mix a polar with a nonpolar, they're just too different. They don't have a way to attract each other, so they stay separate. It's exactly why oil and water just don't mix. So let's tie this all together with one last thought. Imagine a river. The water, of course, is the solvent, and any pollutants in it are the solutes. Now, knowing everything we've just talked about, solvents, solutes, and especially concentration, what do you think happens to the concentration of those pollutants when a drought comes along and the amount of solvent, the water, starts to drop? It's a real-world puzzle, and it shows you just how much this stuff actually matters.